Let's look at the tool of logistic regression from the concept of other approaches we could take to analyze binary outcome variables. We'll see their limitations, and then that will allow us to see why logistic regression is so powerful and so useful. These are some data from low birth weight infants from the Boston area. This is a famous data set that you'll see in a lot of statistical classes. We have N equals 223, and about a third of these kids have a disease called BPD. It's something that you would like to be able to predict and try to give early therapy for it. I'm just going to call it right now the disease or the illness. I don't care what it is. What I care about is it's something that is a yes or a no. You have it or you don't. It's a binary outcome. How do we predict a binary outcome? You might think about if you went in and you said, what's the chance that my baby's going to have this? Or if you said, what is the baseline estimate or the base rate of this thing? Well, it'd be simple. It'd be what percentage of babies have it. So you look at the data and you have this amount that have it and this amount that don't. And you have about a third, 34% have it. So you might think about, can I make a model that's better than 34%? Because in the absence of any mental gymnastics or anything I have to do, I can just say, yeah, there's about a third chance that that baby will have it. Now, you might have some sort of chart or something that might say, how do I summarize data if I have this continuous variable that I'm interested in, this binary outcome? So say we have a research question. How does birth weight relate to having BPD? You might have a little chart that says, hey, Kevin, if you have a binary outcome, if you have a binary variable, and then if you have a continuous variable, you can run a t-test. So you might run a t-test. You might try to fit a linear regression. You might try to get a little bit creative and say, oh man, I don't have anything in my toolbox that predicts a binary outcome from a continuous predictor like birth weight, but I do have something in my toolbox where if I take birth weight and put it into categories, I can see how two categorical variables are related. And that's called a chi-square. So maybe let's recode birth weight into categories 1, 2, and 3. And then let's see if there's a homogeneity of proportions in those categories. These are the smallest babies. These are the biggest babies. These are the babies in the middle. And the probability of having BPD in those groups changes. So we could write an interpretation and say the probability of having the disease if you're in this category, the probability of having the disease if you're in this, the probability of having the disease if you're in this, and it's statistically significant. Now, there's nothing wrong with that at all, and you'll see this done all the time. But as a general rule, don't dumb down your data unless you really have to. You have good information here about the actual birth weight of the baby, and now you're going down the hierarchy and putting it into categories. Don't do that unless you really have to. Let's keep that information. We might, oh, this is funny. I had to spell professor. But professor, I have a chart here that says if I have a binary variable, I have BPD, right? And then I have a continuous variable, birth weight, I should run a t-test. And we could make a t-test here and say the mean birth weight between babies with and without this disease is that much apart. But the problem with running a t-test is here, now you've sort of flipped the research question around. What we're really interested in saying is, for every 1 unit increase in birth weight, how does my probability of this disease change? As birth weight goes up, how does risk change? So this isn't wrong, but it answers a different question than we're really interested. We really would like something that goes beyond the t-test. This t-test here says, hey, there's a significant difference. Look, babies with the disease are smaller, 330 smaller than babies without the disease. Okay, that's well and good, but it still doesn't tell me anything. If I come in and say, what's the probability my baby's going to have it? They can plug in some numbers and make a prediction. It would be really nice. It would be really nice if I had a model like that. Hey, what's my probability of this disease given my birth weight? Then we could talk about the slope. Birth weight is a significant predictor of BPD, or birth weight is not a significant predictor of BPD. We could even do some summary statistics probably. And if you think for a second, you could probably add other slopes or other betas in here, maybe maternal smoking. This would be really nice. we can have Stata try to do something like that if we take all of our points. Remember, the points are interesting because birth weight is here. And then the outcome is you either have it or you don't. So the points are all in a line. Now, we said this before. The great thing about Stata is it will do anything that you tell it to do, but the dangerous thing is it will do anything that you tell it to do. Stata is more than happy to fit a linear model through those points using ordinary least squares, minimizing the sum of the squared residuals, fitting a line that says BPD equals 1.21 plus this times birth weight. Now, it's a model. It predicts something, but the question is, what does it predict? How can we interpret it? In the next set of slides, we'll see how we can actually model the probability of having that binary outcome.